Hello there, and welcome. Tonight we're going on a journey through space to visit some of the most mysterious and powerful objects in the universe. We're talking about black holes, and not just any black holes. We're going to explore the ones that are closest to us right here in our cosmic neighborhood. Now, when I say close, I need to be honest with you. We're still talking about distances that are almost impossible to imagine. The nearest black holes are thousands of light years away, which means even travelling at the speed of light, it would take thousands of years to reach them. But in the grand scale of our galaxy, which stretches about 100,000 light years across, these black holes are practically next door. Before we start our journey, let's make sure we understand what we're looking for. What exactly is a black hole? At its most basic, a black hole is a region of space where gravity is so incredibly strong that nothing can escape from it once it gets too close. Not even light, the fastest thing in the universe, can break free. That's why we call them black holes. They're essentially invisible against the darkness of space. Black holes form when massive stars reach the end of their lives. When a star much bigger than our Sun runs out of fuel, it can no longer support itself against its own gravity. The core collapses in on itself in a catastrophic event we call a supernova, and if enough mass remains, it keeps collapsing until it becomes a black hole. All that mass gets compressed into an incredibly tiny space, creating gravity so intense that it warps the very fabric of space and time around it. Think about it this way. Imagine you could take something as massive as our Sun and squeeze it down to the size of a small city, or even smaller. The gravity at the surface would be absolutely overwhelming. Now imagine something even more extreme, a point where all that mass is compressed into a space smaller than an atom. That's the kind of density we're dealing with at the centre of a black hole. Every black hole has what we call an event horizon. This is the point of no return. Cross this invisible boundary and you're never coming back. The event horizon isn't a physical surface like the ground beneath your feet. It's more like an invisible line drawn in space. On one side, escape is still theoretically possible if you're moving fast enough. On the other side, no amount of speed, no amount of power. Nothing can save you from being pulled into the black hole's centre. So how do we find these invisible objects? If they don't emit light and we can't see them directly, how do astronomers know they're there? This is where things get clever. Black holes might be invisible, but they have visible effects on everything around them. When a black hole has a companion star orbiting nearby, it can pull material away from that star. This stolen matter forms a swirling disk around the black hole, called an accretion disk, and as this material spirals inward, it heats up to millions of degrees and releases intense X-rays. We can detect those X-rays with specialized telescopes, even from thousands of light years away. Scientists also watch for stars that seem to be orbiting around nothing. When we see a star moving in an orbit, circling around empty space, we know something massive must be there, pulling on it with gravity. By measuring how the star moves, we can calculate the mass of whatever it's orbiting. If that mass is compressed into a small enough space, and if it doesn't emit any light, we can be pretty confident we're looking at a black hole. Now, let's begin our journey. We'll start with the absolute closest black holes to Earth and work our way out from there, visiting some of the most fascinating objects in our local galactic neighborhood. Our first stop takes us about 1,600 light years away to a system called Gaia BH1. Discovered in 2022, this black hole holds the current record as the closest known black hole to Earth. It's roughly 10 times the mass of our Sun, making it what we call a stellar mass black hole, the kind that forms when a single massive star collapses. What makes Gaia BH1 particularly interesting is that it's part of a binary system. It has a companion star, a Sun-like star that orbits around their common centre of mass. The European Space Agency's Gaia spacecraft, which is mapping the positions and movements of billions of stars in our galaxy, detected something odd about this star's motion. The star was wobbling in its path across the sky in a very specific way, as if it were orbiting around something massive that we couldn't see. Scientists followed up with detailed observations and measurements. They tracked the star's motion carefully over time, and the data told them something remarkable. This star was orbiting a black hole. By measuring the orbit, they could calculate that the unseen companion had to be about 10 solar masses, and the nature of the orbit told them it had to be compact, far too small to be a normal star of that mass. The conclusion was clear. This was a black hole. What's particularly notable about Gaia BH1 is that it's what we call a dormant or quiescent black hole. It's not actively feeding on material from its companion star, so it's not producing the bright X-rays that make many black holes easier to spot. It's just sitting there, quietly pulling on its companion with gravity, otherwise minding its own business in the darkness of space. This makes it harder to find, but also more representative of what most stellar mass black holes in the galaxy might be like. How does it feel to know that there's a black hole this close to us? Well, before you worry, 1,600 light-years is still an enormous distance. For perspective, the nearest star to our Sun is only about 4 light-years away, and our entire solar system could fit comfortably within a light day or so. Gaia BH1 is so far away that it has absolutely no effect on Earth or our solar system. Its gravity diminishes with distance, just like any other object's gravity, and from where we are, it's essentially unnoticeable. Let's continue our journey to our next destination, about 1,126 light-years away. This is Gaia BH2, discovered in 2023, making it the second closest known black hole to Earth. Like its closer cousin, Gaia BH2 was also found by analysing data from the Gaia spacecraft, and it too is a dormant black hole in a binary system with a companion star. Gaia BH2 is even more massive than Gaia BH1, weighing in at roughly 9 times the mass of our Sun. Its companion star is a red giant, a star that has aged and expanded to many times its original size. The two objects orbit their common centre of gravity every 1,277 days, or about 3.5 years. The discovery of Gaia BH2 came from the same detective work that revealed Gaia BH1. Astronomers noticed that this red giant star was moving in a peculiar way, as if dancing with an invisible partner. By carefully measuring its motion and applying the laws of gravity and orbital mechanics, they could determine that the invisible partner was a black hole. These discoveries are particularly exciting because they suggest something important. There are likely many more black holes like these scattered throughout our galaxy, black holes that aren't actively feeding and therefore aren't announcing their presence with bright X-rays. Scientists currently estimate that there could be tens of millions or even hundreds of millions of stellar mass black holes in the Milky Way galaxy alone. Most of them are probably sitting quietly in the darkness, detectable only by their gravitational influence on nearby stars. Moving a bit farther out, let's talk about a system that was, for a time, thought to be the closest black hole to Earth, before Gaia BH1 and BH2 were discovered. This is the system called V6116 Monocerotis, also known as Aoeroa 620 Weiro, located roughly 3,000 light-years away in the constellation Monoceros. V616 Monocerotis is different from the Gaia black holes in an important way. It's an active X-ray binary. This black hole, which is between 5 and 10 solar masses, has a companion star that's smaller than our Sun. The black hole is actively pulling material from this companion, and that material forms an accretion disk that occasionally flares up and releases intense X-rays that we can detect here on Earth. This system was first discovered in 1975 when it underwent an X-ray outburst, a dramatic brightening that made it temporarily one of the brightest X-ray sources in the sky. During these outbursts, material from the companion star crashes into the accretion disk at tremendous speeds, heating up to millions of degrees and releasing enormous amounts of energy. What can we learn from a system like this? Quite a lot, actually. When material spirals into a black hole's accretion disk, it doesn't fall straight in. It orbits faster and faster as it gets closer. Just like water spiraling down a drain, but moving at a significant fraction of the speed of light. The friction between different layers of material in the disk generates tremendous heat, and this is what produces the X-rays we detect. By studying how these X-rays vary over time, scientists can learn about the structure of the accretion disk, how material flows through it, and even about the properties of the black hole itself. The pattern of X-ray emission can tell us about the black hole's mass, its spin rate, and how the space around it is warped by gravity. Let's venture a bit farther now, to about 3,000 to 6,000 light-years away, to visit Cygnus X1, one of the most famous and well-studied black holes in our galaxy. Cygnus X1 holds a special place in the history of astronomy. It was the first object to be widely accepted as a black hole, and its discovery and confirmation opened up an entirely new field of research. The system consists of a black hole roughly 21 times the mass of our Sun and a massive blue supergiant star about 40 times the Sun's mass. The story of Cygnus X1's discovery is fascinating. In the 1960s, scientists launched the first X-ray observatories into space, and they quickly discovered numerous sources of X-rays coming from beyond our solar system. One of the strongest sources was in the constellation Cygnus, so they named it Cygnus X1. But what was producing these X-rays? Astronomers pointed their optical telescopes at the same region of sky and found a blue supergiant star. By watching this star carefully, they noticed it was wobbling, moving in an orbit around something they couldn't see. They measured the wobble and calculated that whatever the star was orbiting had to be incredibly massive and incredibly compact. The unseen companion was too massive to be a neutron star, another type of extremely dense object that can form when massive stars die. Here's where it gets interesting from a historical perspective. In 1974, two famous physicists, Stephen Hawking and Kip Thorne, made a bet about whether Cygnus X1 really contained a black hole. Hawking bet against it being a black hole, while Thorne bet for it. Hawking later explained that he made this bet as a kind of insurance policy. If black holes didn't exist, at least he'd win the bet and have something to feel good about. But as evidence accumulated over the years, it became increasingly clear that Cygnus X1 really was a black hole. Hawking conceded the bet in 1990, acknowledging that the evidence was overwhelming. What makes Cygnus X1 particularly interesting is that it's what we call a high-mass X-ray binary. The companion star is so massive and so bright that it's producing a powerful stellar wind, a stream of gas flowing outward from its surface. The black hole intercepts some of this wind, and as the captured gas spirals into the accretion disk, it produces the X-rays we detect. Scientists have studied Cygnus X1 intensively for decades, and it's taught us an enormous amount about how black holes behave when they're actively feeding. The system produces not just X-rays, but also jets, narrow beams of matter and energy that shoot out perpendicular to the accretion disk at speeds approaching the speed of light. These jets are one of the most dramatic phenomena associated with black holes, and we're still working to fully understand how they form and how they're powered. Recent studies have also measured the spin of the black hole in Cygnus X1. Yes, black holes spin, and they can spin incredibly fast. The black hole in Cygnus X1 is rotating at more than 95% of the maximum possible spin rate. This spin warps the space around the black hole in complex ways and can influence how material flows through the accretion disk. As we continue our journey outward, we reach about 6,000 to 7,000 light-years to visit V404 Cygni. Another famous black hole system in the constellation Cygnus. V404 Cygni is roughly 9 times the mass of our Sun, and it has a companion star about half as massive as the Sun. What makes this system special is its dramatic and unpredictable behaviour. Most X-ray binaries are relatively steady or have predictable patterns of outbursts. V404 Cygni, on the other hand, is wild and chaotic. The system was first detected as an X-ray source in 1989 when it underwent a major outburst. Then it went quiet for 26 years, barely producing any X-rays at all. But in June 2015, it erupted again in one of the most spectacular black hole outbursts ever observed. For several weeks, V404 Cygni was one of the brightest X-ray sources in the sky, and astronomers around the world have scrambled to observe it with every telescope they could point at it. What was so remarkable about this outburst? Unlike most black hole systems, which show relatively smooth changes in brightness, V404 Cygni's brightness was fluctuating wildly and rapidly. On timescales of minutes or even seconds, its X-ray emission would change by factors of hundreds or thousands. The system would go from extremely bright to relatively dim, and back again in the blink of an eye. Why does V404 Cygni behave this way? Scientists think it has to do with the structure of its accretion disk. Evidence suggests that the disk in this system is unusually thick and puffy, and it might be tilted or warped relative to the black hole's equator. When material flows through such a disk, it can create instabilities and turbulence that cause the dramatic and rapid variations in brightness we observe. This system has taught us that not all black holes behave the same way, even when they're in similar situations with companion stars. The specific details, the mass of the black hole, the spin rate, the nature of the companion star, the alignment of the orbit, all these factors can influence how the system behaves. Now let's talk about something that has puzzled and fascinated astronomers for years. If we look at the centre of our own Milky Way galaxy, about 26,000 light-years away, we find something extraordinary, a supermassive black hole called Sagittarius A, or SGR-A for short. Wait, you might be thinking, I thought we were talking about our closest black holes. Why are we jumping all the way to the centre of the galaxy? Well, here's the thing. While Sagittarius A is much farther away than the stellar mass black holes we've been discussing, it's fundamentally different. This isn't a black hole formed from a single collapsing star. It's a monster that weighs about 4 million times the mass of our Sun. Supermassive black holes like Sagittarius A are found at the centres of most large galaxies, and scientists are still working to fully understand how they form. They're too massive to have formed from a single star, no matter how large. Instead, evidence suggests they may have grown over billions of years by consuming gas, dust and stars, and by merging with other black holes. How do we know Sagittarius A is there? We can't see the black hole itself, of course, but astronomers have been tracking the orbits of stars near the galactic centre for decades. These stars are moving incredibly fast, orbiting at speeds of thousands of kilometers per second. One star, called S2, orbits so close to the black hole that it completes one orbit in just 16 years, even though its orbit takes it as far as 1,000 times the distance between Earth and the Sun. By watching these stars over many years, scientists have created a detailed map of their orbits, and those orbits all point to one conclusion. There must be something incredibly massive at the very centre, something with a mass of about 4 million suns compressed into a region smaller than our solar system. The only object that fits this description is a supermassive black hole. In 2022, scientists achieved something remarkable. They actually captured an image of Sagittarius A. Well, not exactly an image of the black hole itself, but an image of the glowing material in the accretion disk around it. Using a network of radio telescopes spread across the entire Earth, working together as one giant telescope through a technique called Very Long Baseline Interferometry, researchers created an image showing a bright ring of emission with a dark center, the shadow of the black hole. This was an incredible achievement. The black hole appears very small in the sky, even though it's enormous by any normal standard. From our perspective, 26,000 light-years away, Sagittarius A appears about the same size as a donut sitting on the moon would appear from Earth. To image something that small required extraordinary precision and coordination. What's it like near Sagittarius A? The environment around our galaxy's central black hole is unlike anything we experience in our quiet neighborhood out here in the spiral arms. The region near the galactic center is crowded with stars, many of them massive and bright, all orbiting in the intense gravitational field of the black hole. There are regions of intense radiation, powerful magnetic fields, and high-energy particles streaming through space. Interestingly, Sagittarius AI is relatively quiet for a supermassive black hole. It's not actively consuming large amounts of material right now, so it's not producing the intense radiation we see from the supermassive black holes in many other galaxies. It's sort of like the stellar mass black holes Gaia BH1 and BH2, present and massive, but not particularly active at the moment. This brings up an interesting question. Could our galactic center black hole become more active in the future? The answer is yes. In fact, there's a cloud of gas called GUO that had a close encounter with Sagittarius A a few years ago. Astronomers watched carefully to see if the black hole would consume this gas and flare up. But while there was some increased activity, it was less dramatic than some had predicted. The black hole may have consumed some of the gas, but much of it survived the encounter. Let's think about what life might be like if Earth were closer to Sagittarius A. Could planets exist near a supermassive black hole? Could they support life? These are fascinating questions that scientists have started to explore. In principle, planets could orbit a supermassive black hole, just as they orbit a star. If the orbit is far enough away, the black hole's gravity would simply act like the gravity of any other massive object. In fact, in some ways, a supermassive black hole might be a more stable anchor for a planetary system than a star, because the black hole doesn't undergo the changes and eventual death that stars experience. However, there are challenges. A planet near the galactic center would be exposed to intense radiation from the crowded stellar environment and from other phenomena in that region. It would also have to contend with frequent gravitational perturbations from nearby stars. The habitable zone around a black hole, the distance where conditions might allow for liquid water, would depend on other sources of energy, since the black hole itself doesn't produce the light and heat that a star does. Some scientists have speculated about planets that might orbit close enough to an accretion disk to receive heat and light from the disk's glow, much as planets in our solar system receive energy from the sun. This is highly speculative, but it's an interesting thought experiment about the diversity of possible planetary environments in the universe. Before we continue our journey, let's pause and think about something profound. Black holes challenge our everyday intuitions about reality in fundamental ways. They're regions where the laws of physics as we normally experience them break down or behave in extremely unusual ways. Near a black hole's event horizon, time itself flows differently than it does far away in normal space. This isn't just a theoretical curiosity, it's a real, measurable effect called gravitational time dilation. If you could hover near the event horizon of a black hole and then return to normal space, you'd find that more time had passed for everyone else than had passed for you. You would have effectively travelled into their future. This happens because gravity warps not just space, but also time. The stronger the gravitational field, the slower time flows relative to regions with weaker gravity. This effect has been measured in experiments on Earth and with satellites in orbit, but near a black hole, it becomes extreme. Imagine two observers, one hovering just outside the event horizon of a black hole, and one watching from a safe distance, far away. If the close observer drops something toward the black hole, they see it fall inward and cross the event horizon in a finite amount of time. But the distant observer sees something different. To them, the falling object appears to slow down as it approaches the event horizon, taking longer and longer to fall each centimetre. The object's light becomes increasingly redshifted, shifting toward longer wavelengths and becoming dimmer. To the distant observer, the object never quite seems to reach the event horizon. It just fades away asymptotically, getting dimmer and slower forever. Both observers are seeing something real. There's no contradiction here, just a demonstration that in the warped space-time near a black hole, different perspectives can see very different things. This is one of the mind-bending implications of Einstein's general theory of relativity. What happens if you fall into a black hole? This is a question people often ask, and the answer depends on the size of the black hole and where you are in your fall. If you were to fall into a stellar mass black hole like the ones we've been discussing, you'd face something called spaghettification, a term that's actually used in scientific literature. As you fall toward the black hole, the gravitational pull on the parts of your body closest to the black hole would be significantly stronger than the pull on the parts farther away. This difference in gravitational pull would stretch you vertically and squeeze you horizontally, pulling you into an increasingly long and thin shape, like a piece of spaghetti. For a stellar mass black hole, this spaghettification would kill you long before you reach the event horizon. The tidal forces would tear your body apart at the molecular level. It wouldn't be a pleasant way to go. Interestingly, for a supermassive black hole like Sagittarius A, things would be different. The event horizon of a supermassive black hole is much larger than that of a stellar mass black hole. Because the black hole's mass is spread out over a larger region, the tidal forces at the event horizon are actually much weaker. You could theoretically cross the event horizon of a supermassive black hole without being torn apart. Of course, that doesn't mean you'd survive. Once you cross the event horizon, there's no coming back. Every possible path you could take, every direction you could move, leads inexorably inward toward the singularity at the centre. And as you fall inward past the event horizon, the tidal forces would grow stronger and stronger until even a supermassive black hole would eventually spaghettify you. What's at the very centre of a black hole? This is one of the deepest unsolved problems in physics. According to general relativity, the centre of a black hole is a singularity, a point where density becomes infinite and the curvature of space-time becomes infinite. But most physicists suspect that this is where general relativity breaks down and needs to be replaced by a theory that combines general relativity with quantum mechanics. We don't yet have a complete theory of quantum gravity, so we can't really say what happens at the centre of a black hole. It might not be a singularity at all. It might be something else entirely, something we don't have the physics to describe yet. This is one of the frontiers of modern physics, and solving it will probably require new insights into the fundamental nature of reality. Let's get back to our journey and talk about some other nearby black hole systems that have taught us important lessons about these objects. About 7,000 to 8,000 light-years away, we find GRS 1915 Plus O5, a black hole system that's remarkable for several reasons. The black hole itself is roughly 10 to 18 times the mass of the Sun, making it one of the most massive stellar mass black holes known in our galaxy. It has a companion star that's about 1.2 times the mass of the Sun. GRS 1915 Sun 05 was discovered in 1992 and immediately attracted attention because of its unusual behaviour. It's one of the most variable X-ray sources in the sky, exhibiting complex patterns of brightening and dimming that can change on timescales from seconds to months. Scientists have identified more than a dozen different patterns of variability in this system, and researchers are still working to understand what causes all these different behaviors. One of the most interesting things about GRS 1915 plus 105 is its jets. This system produces some of the most powerful and dramatic jets ever observed from a stellar mass black hole. These jets are launched perpendicular to the accretion disk and travel at more than 90% of the speed of light. By watching these jets over time, astronomers have been able to study how they form, how they're collimated into narrow beams, and how they interact with the surrounding space. The jets from GRS 1915 plus 105 have also helped scientists test Einstein's special theory of relativity in extreme conditions. When something moves towards you at close to the speed of light, it can appear to be moving faster than light due to a projection effect. The jets from this system provided some of the clearest early examples of this superluminal motion, helping to confirm our understanding of relativistic physics. Another fascinating nearby system is GX 339-4, located roughly 10,000 light-years away. This black hole, which is about 8 times the mass of the Sun, has a low-mass companion star, and the system regularly goes through cycles of outburst and quiescence. What makes GX 339-4 particularly valuable for research is that it's relatively close and undergoes frequent outbursts, providing many opportunities for detailed study. The system has become a sort of laboratory for understanding how black holes transition between different states of activity. Black hole X-ray binaries can exist in several different states, characterized by different patterns of X-ray emission and different behaviors of the accretion disk and jets. In the low hard state, the system produces relatively low levels of X-rays with a particular spectral signature, and steady jets are often present. In the high soft state, the X-ray emission is much brighter but with a different spectral signature, and the jets usually turn off. Why do these states exist, and why do systems transition between them? Scientists think it has to do with changes in the rate at which matter flows into the black hole and how the accretion disk behaves at different accretion rates. When the accretion rate is relatively low, the disk might be hot and geometrically thick, with some of the material being launched in jets rather than falling into the black hole. When the accretion rate is high, the disk becomes cooler and geometrically thinner, and the jets shut down as more material funnels directly into the black hole. GX 339-4 has been observed transitioning between these states multiple times, and each time scientists learn more about the physics driving these changes. Understanding these state transitions is important not just for stellar mass black holes, but also for understanding supermassive black holes in distant galaxies, which undergo similar transitions but on much larger scales. Let's talk about another type of system that involves black holes: ultra-compact binaries. These are systems where a black hole has a companion star that's very close, orbiting in hours rather than days or weeks. One example is XTE J1180, located roughly 6,000 light-years away. In this system, a black hole of about 8 solar masses orbits with a low-mass companion star every 4.1 hours. That's an incredibly short orbital period, which tells us the two objects must be very close together. The entire orbit would fit comfortably inside our Sun. Ultra-compact systems like this are interesting because they're strong sources of gravitational waves, ripples in space-time itself that propagate outward at the speed of light. While stellar mass black holes orbiting each other produce gravitational waves that we can detect with instruments like LIGO, ultra-compact X-ray binaries produce gravitational waves at lower frequencies that future space-based detectors should be able to observe. These systems are also losing energy and angular momentum over time due to gravitational wave emission, causing the orbit to slowly shrink. Eventually, Over millions or billions of years, the black hole will consume the companion star entirely. This gradual spiral provides another way to study how black holes and their companions interact. Speaking of gravitational waves, let's talk about one of the most exciting developments in black hole astronomy in recent years. In 2015, the LIGO observatories in the United States detected gravitational waves for the first time, and the waves came from two black holes merging together about 1.3 billion light-years away. Now, 1.3 billion light-years is far beyond what we'd call our neighbourhood, but this discovery opened up an entirely new way of observing black holes. Before gravitational wave astronomy, we could only detect black holes if they were doing something that produced electromagnetic radiation, X-rays, visible light, radio waves, and so on. But gravitational waves allow us to detect black holes even when they're not emitting any light at all. Since 2015, LIGO and its partner observatory Virgo have detected dozens of black hole mergers. These events happen when two black holes in a binary system spiral inward toward each other, eventually colliding and merging into a single, larger black hole. The merger releases an enormous amount of energy in the form of gravitational waves. In some cases, more energy than all the stars in the visible universe are emitting at that moment. Though that energy is released as gravitational waves rather than light. What can we learn from these mergers? Quite a lot. Each detection tells us about the masses of the merging black holes, their spins, and how those spins are oriented relative to the orbital plane. We're learning that stellar mass black holes can be more massive than we previously thought. Some of the black holes detected by LIGO are more than 30 or even 50 times the mass of the Sun, which was surprising because theoretical models hadn't predicted that single stars could collapse to form such massive black holes. Some scientists think these very massive black holes might form through a different pathway. Instead of forming from a single collapsing star, they might be the product of earlier black hole mergers, or they might form in dense stellar environments where multiple stars can merge before collapsing. This is an active area of research, and gravitational wave observations are helping to answer these questions. The mergers detected by LIGO and Virgo also provide the strongest tests we've ever had of general relativity in extreme conditions. Einstein's theory predicts very specific patterns for how gravitational waves should look, depending on the masses and spins of the merging black holes. So far, every detection has been consistent with general relativity's predictions, showing that the theory remains valid even in these incredibly extreme environments. Now you might wonder, could we ever visit a black hole? Could we send a spacecraft to study one up close? In principle, yes, though there are enormous practical challenges. The closest known black holes are thousands of light years away, and with our current technology, we have no way to travel such distances in a reasonable amount of time. Our fastest spacecraft, like the Voyager probes, are travelling at about 17 kilometers per second relative to the Sun. At that speed, it would take roughly 100,000 years to travel just one light year, and tens of millions of years to reach even the nearest black holes. But let's imagine we had some future technology that could accelerate a spacecraft to a significant fraction of the speed of light. Could we safely study a black hole up close? Well, it depends on what you mean by up close. If you wanted to study the environment near the event horizon, you'd need to contend with several challenges. The intense gravitational field would make navigation difficult, and any slight miscalculation could send your spacecraft tumbling past the event horizon. The tidal forces would grow stronger as you approached, potentially damaging or destroying the spacecraft. If the black hole has an accretion disk, the environment would be filled with intense radiation and high-energy particles that could damage electronics and harm any astronauts on board. However, studying a black hole from a safe distance would be much more feasible. You could park your spacecraft at a distance where the gravity is strong enough to be interesting but not dangerous. Observe the black hole's effects on nearby matter and light, and measure the warping of spacetime around it. This would give us an unprecedented view of general relativity in action. Some scientists have even speculated about using black holes as tools. For example, if you could somehow harness the rotational energy of a spinning black hole, you could potentially extract enormous amounts of power. This idea, called the Penrose process after physicist Roger Penrose, who proposed it, involves dropping material into a specific region just outside the event horizon, where it can interact with the black hole's rotation and emerge with more energy than it started with. Another speculative idea is using a black hole's extreme gravity as a gravitational slingshot to accelerate spacecraft to very high speeds. This is similar to how we use planetary gravity assists today, but on a much more extreme scale. Of course, all of this is purely theoretical at present, and we're a very long way from having the technology to attempt it. Let's think about the broader context of black holes in our galaxy and in the universe. How many black holes are there? How are they distributed? And what role do they play in the evolution of galaxies? As I mentioned earlier, scientists estimate there could be tens of millions or even hundreds of millions of stellar mass black holes in the Milky Way galaxy alone. Most of them are probably sitting quietly in the dark, detectable only by their gravitational influence if they happen to be in a binary system with a visible star. These black holes formed over the history of our galaxy as massive stars lived out their lives and died in supernova. The rate of black hole formation depends on the rate at which massive stars form, and this has varied over cosmic time. In the early universe, shortly after the first stars formed, there was a burst of massive star formation, which would have produced many black holes. The rate has generally declined over time, though it still continues today wherever massive stars are being born. Supermassive black holes, like Sagittarius A at the centre of our galaxy, have a different story. Evidence suggests that most or all large galaxies have supermassive black holes at their centres, and these black holes grow along with their host galaxies in complex ways. When galaxies merge, which happens frequently in the universe, their central black holes eventually sink to the centre of the merged galaxy and orbit each other, eventually merging themselves. This process can create black holes with masses of millions or even billions of times the Sun's mass. The relationship between supermassive black holes and their host galaxies is one of the most interesting puzzles in modern astrophysics. Observations have shown that there's a tight correlation between the mass of a galaxy's central black hole and properties of the galaxy itself, such as the mass of its central bulge of stars. This suggests that black holes and galaxies somehow influence each other's growth, even though the black hole is tiny compared to the galaxy as a whole. How does this connection work? Scientists think that black holes can influence their host galaxies through a process called feedback. When a supermassive black hole is actively feeding, consuming large amounts of gas and dust, it doesn't just produce radiation, it can also drive powerful winds and jets that push gas out of the galaxy, or heat it up so much that it can't collapse to form new stars. This feedback can regulate star formation in the galaxy, preventing it from turning all its gas into stars too quickly. This might sound strange, a black hole that's only a tiny fraction of the galaxy's mass, somehow controlling what happens in the entire galaxy. But the key is energy. An actively feeding supermassive black hole releases enormous amounts of energy, and even though the black hole itself is small, this energy can have galaxy-wide effects. We can see this process in action in many galaxies across the universe. Some of the most luminous objects in the universe are quasars, supermassive black holes that are feeding so voraciously that they outshine their entire host galaxies. The energy from these quasars can be detected from billions of light years away. Our own Sagittarius A is relatively quiet now, but evidence suggests it was much more active in the past and could become active again in the future. Now let's explore some of the stranger predictions about black holes, things that stretch our understanding of physics even further. One of the most famous predictions about black holes comes from Stephen Hawking, who showed in 1904 that black holes aren't actually completely black. Through a quantum mechanical process now called Hawking radiation, black holes should emit a very faint glow of particles and slowly lose mass over time. This means that black holes can actually evaporate, though the process is extraordinarily slow for black holes of stellar mass or larger. How does Hawking radiation work? It's based on quantum mechanics, which tells us that what we think of as empty space isn't really empty. It's full of quantum fluctuations, with pairs of particles and antiparticles constantly popping into existence and annihilating each other. Usually, these virtual particles exist for such a brief time that they have no observable effect. But near a black hole's event horizon, something interesting can happen. If a particle-antiparticle pair forms right at the event horizon, one particle might fall into the black hole while the other escapes. To an outside observer, it looks like the black hole has emitted a particle. This process carries away energy, which means the black hole loses mass. For a stellar mass black hole, Hawking radiation would be incredibly faint, far too faint to detect with any current technology. The black hole would gain more mass by absorbing the cosmic microwave background radiation from the Big Bang than it would lose through Hawking radiation. But if we wait long enough, an incomprehensibly long time, far longer than the current age of the universe, eventually all the matter and radiation in the universe would thin out, and black holes would begin to evaporate in earnest. A stellar mass black hole would take about 10 to the 67 years to evaporate completely through Hawking radiation. That's a 1 followed by 67 zeros, an unimaginably long time. For comparison, the universe is currently only about 13.8 billion years old, which is about 10 to the power 10 years. Supermassive black holes would take even longer, roughly 10 to the 100 years, for a black hole a billion times the mass of the Sun. As a black hole evaporates, it gets hotter and radiates faster. The final stages of evaporation would happen very quickly, with the black hole releasing its remaining mass in a burst of radiation. Of course, no black hole in the current universe has had time to evaporate yet, and none will for an inconceivably long time. But this process shows that black holes aren't the eternal, unchanging objects they might seem at first. Hawking radiation also creates an interesting puzzle called the black hole information paradox. In quantum mechanics, information is supposed to be conserved. It can be transformed, but never truly destroyed. But if a black hole evaporates completely through Hawking radiation, what happens to all the information about the matter that fell into it? Does it disappear, violating quantum mechanics? Is it somehow encoded in the Hawking radiation, or is something else going on? This paradox has occupied some of the greatest minds in theoretical physics for decades, and while progress has been made, there's still no consensus on the complete answer. Some proposals suggest that information is somehow encoded on the black hole's event horizon, or that it's released in subtle correlations in the Hawking radiation. Others suggest that we need a deeper understanding of quantum gravity to resolve the paradox. This remains one of the most important unsolved problems in theoretical physics. Let's talk about another exotic prediction: wormholes. In science fiction, wormholes are often portrayed as shortcuts through space that connect distant parts of the universe. Could they really exist? The short answer is maybe, but probably not in any useful way. General relativity does allow for solutions called Einstein-Rosen bridges, which are sometimes called wormholes. These are connections between two different regions of spacetime. In principle, You could enter one end and emerge from the other end, which might be in a different location or even a different time. However, there are several major problems with wormholes. First, the solutions that describe them typically involve exotic matter with negative energy density, something we've never observed and that may not exist in nature. Second, wormholes in these solutions are generally unstable. They would collapse before anything could pass through them. Third, even if a stable wormhole could exist, traversing it might not actually be faster than traveling through normal space, depending on the geometry. Some scientists have explored whether a sufficiently advanced civilization could create and stabilize a wormhole, perhaps using as yet unknown physics. This remains highly speculative, and most physicists suspect that various physical constraints would prevent traversable wormholes from existing, but it's an interesting area where general relativity allows for possibilities that seem strange from our everyday perspective. Black holes might also be related to white holes, hypothetical objects that are the time-reversed version of black holes. While a black hole is a region where nothing can escape, a white hole would be a region where nothing can enter. Matter and light would only flow outward. White holes appear in some solutions to Einstein's equations, but there's no evidence that they exist in nature, and they raise serious questions about causality and the arrow of time. Another fascinating aspect of black holes involves their connection to string theory and other theories that attempt to unify quantum mechanics and gravity. In string theory, black holes can be described as bound states of fundamental objects, called branes. This approach has led to some remarkable calculations, including an explanation for the entropy of black holes, a measure of how many different microscopic configurations could give rise to the same macroscopic black hole. The fact that string theory can reproduce results about black hole entropy that were originally derived using completely different methods is seen by many physicists as encouraging evidence that string theory might be on the right track as a theory of quantum gravity. However, string theory remains unproven, and we currently have no experimental way to test most of its predictions. Let's return to the black holes in our cosmic neighborhood and think about what future discoveries might await us. New observational techniques are constantly improving our ability to find and study black holes. The Gaia spacecraft, which discovered Gaia BH1 and BH2, is still operating and mapping the galaxy. Scientists expect it will find more nearby black holes as they continue to analyze the data. There could be even closer black holes waiting to be discovered, perhaps even some within 1,000 light-years of Earth. Gravitational wave observatories are also being upgraded and expanded. LIGO and Virgo are being joined by additional detectors, including KAGRA in Japan, and plans for future observatories in India and Australia. Having more detectors around the world allows for better localization of gravitational wave sources and more precise measurements of the merging black hole's properties. In the future, we might have space-based gravitational wave observatories like LISA, the Laser Interferometer Space Antenna, which is planned for launch in the 2030s. LISA would be sensitive to gravitational waves at lower frequencies than LIGO, allowing it to detect supermassive black hole mergers from across the universe and ultra-compact binaries in our own galaxy. This would open up an entirely new window on the universe of black holes. New X-ray telescopes are also being planned and built. These will be more sensitive than our current instruments and able to observe fainter sources and study the behavior of black holes in greater detail. They'll help us understand the physics of accretion disks, jets, and the extreme environments near black holes. Radio telescope arrays are becoming more capable as well. The Event Horizon Telescope collaboration, which imaged Sagittarius A and the supermassive black hole in galaxy M87, is working to improve its resolution and extend its capabilities. Future observations might allow us to see the environment around black holes in even greater detail and perhaps even detect changes over time. There's also the possibility of detecting intermediate mass black holes, a category we haven't discussed much yet. These would be black holes with masses between stellar mass black holes and supermassive black holes, perhaps hundreds or thousands of times the mass of the Sun. Scientists have found some candidate intermediate mass black holes, but confirmed detections are still relatively rare. These objects might form in dense star clusters or through the merger of multiple stellar mass black holes, and finding more of them would help us understand how supermassive black holes grew to their enormous sizes. What about the possibility of primordial black holes? Black holes that might have formed in the very early universe, shortly after the Big Bang, rather than from collapsing stars. If conditions were right in certain regions of the early universe, matter could have been compressed enough to form black holes with masses ranging from microscopic to thousands of solar masses. Primordial black holes are hypothetical, but they're interesting for several reasons. First, they could potentially explain dark matter, the mysterious substance that makes up about 85% of the matter in the universe, but doesn't emit, absorb, or reflect light. If primordial black holes exist in large numbers, they could account for at least some of the dark matter. However, various astronomical observations have placed strong constraints on how many primordial black holes can exist at different mass ranges, and most scientists now think they probably don't make up a large fraction of dark matter. Second, primordial black holes could have played a role in seeding the formation of supermassive black holes. If primordial black holes formed early enough, they could have served as the starting points around which the first supermassive black holes grew. Searching for primordial black holes is challenging because they're predicted to be rare, and if they're small enough, they might not produce observable effects. However, if they exist, they might occasionally pass through our solar system, and their gravitational influence could potentially be detected through precise observations of the orbits of planets and spacecraft. Another exciting area of research involves studying the space around black holes in even greater detail. The region just outside the event horizon, sometimes called the near horizon region, is where the effects of strong gravity are most extreme. By studying the light from hot gas orbiting in this region, scientists can test general relativity in ways that aren't possible anywhere else. One specific prediction of general relativity that scientists are working to observe directly is called the Innermost Stable Circular Orbit, or ISCO. This is the closest orbit around a black hole where matter can stably circle without inevitably spiraling inward. The location of the ISCO depends on the black hole's spin. It's closer to the event horizon for a rapidly spinning black hole and farther out for a slowly spinning one. By identifying the ISCO in observations of accretion disks, scientists can measure how fast black holes are spinning. Black hole spin is important for several reasons. It affects how much energy can be extracted from the black hole's rotation, it influences the behavior of the accretion disk and jets, and it carries information about the black hole's history. A black hole that formed from the collapse of a single star might spin differently than one that grew by merging with other black holes or by accreting matter from a specific direction over time. Let's think about some of the philosophical implications of black holes. What do they tell us about the nature of reality, space, time, and the limits of knowledge? Black holes represent regions of space-time that are fundamentally disconnected from the rest of the universe. Once something crosses the event horizon, no signal it sends can ever reach us. This creates what's called a cosmic censorship. We can never see what happens at the singularity or inside the event horizon. The event horizon literally censors information about the interior of the black hole. This raises interesting questions about the nature of physical law. Can physical laws apply to regions we can never observe? Can we meaningfully talk about what exists inside a black hole if we can never verify it empirically? These questions touch on deep issues in the philosophy of science about the relationship between theory and observation. Black holes also challenge our intuitions about time. For someone falling into a black hole, time continues normally. They cross the event horizon at a definite moment and continue inward. But for someone watching from outside, they never see the person cross the horizon. Time literally stops at the event horizon from the outside observer's perspective. Both perspectives are valid within their own reference frames, showing that time isn't absolute but depends on your state of motion and the gravitational field you're in. At the singularity in a black hole's center, if it truly exists, time and space switch roles in a certain sense. Outside the event horizon, you can move freely through space but are always dragged forward through time. Inside the event horizon, you can move freely through time in a sense, but all paths through space lead to the singularity. This inversion of the roles of space and time is one of the most bizarre predictions of general relativity. These strange features of black holes have led some physicists to speculate about connections between black holes and the nature of consciousness, information, and even the structure of the universe as a whole. While many of these ideas are highly speculative, they show how black holes push us to think deeply about fundamental concepts we usually take for granted. Now, as we near the end of our journey, let's consider what might happen in the far future, in a universe where black holes are the dominant objects. Stars won't shine forever. They burn through their fuel, and eventually all the gas in galaxies will either be incorporated into stars that burn out or be ejected from galaxies by various processes. In the extremely distant future, perhaps 10 to 14 years from now, that's 100 trillion years, more than 7,000 times the current age of the universe, star formation will essentially cease. After that, the universe will enter what's called the degenerate era, where the main objects are dead stars, white dwarfs, neutron stars, and black holes, along with planets, asteroids, and other cold debris. Over even longer timescales, roughly 10 to 40 years, these objects will gradually fall into the supermassive black holes at the centers of galaxies through gravitational interactions and rare collisions. Eventually, after about 1,000 years, the black hole era will end as well. All black holes, even supermassive ones, will eventually evaporate through Hawking radiation, leaving behind only a thin soup of elementary particles in an ever-expanding universe. This final era, sometimes called the dark era, would last essentially forever, with the universe becoming ever colder, ever emptier, ever darker. Of course, these are projections based on our current understanding of physics, and that understanding might change. There could be processes we don't know about that would alter this timeline. But based on what we currently know, black holes will outlast stars, planets, and galaxies, persisting as the last massive objects in the universe before they too fade away. This cosmic eschatology, the study of the ultimate fate of the universe, might seem depressing, but it's also awe-inspiring in its own way. It shows the vast scales of time and space that physics allows us to explore, reaching far beyond human timescales or even the lifetime of stars. Let's bring our journey back to Earth and think about what black holes mean for us, here and now, in our everyday lives. You might wonder, why should we care about black holes? They're far away. They don't affect us directly, and we'll never visit one. What's the point of studying them? There are several answers to this question. First, black holes are laboratories for testing our understanding of fundamental physics. The extreme conditions near black holes allow us to test general relativity and quantum mechanics in ways we can't do anywhere else. Studying black holes helps us refine and improve our theories of how the universe works at the most fundamental level. Second, black holes play an important role in the evolution of galaxies and thus in the history of the universe. Understanding how black holes influence star formation and galaxy evolution helps us understand our own cosmic origins. The atoms in our bodies were forged in stars, and the history of star formation is intimately connected with the history of black holes. Third, the technology developed to study black holes has applications beyond astronomy. Techniques developed for detecting gravitational waves, processing data from radio telescope arrays, and analyzing complex astrophysical phenomena have found uses in fields ranging from medical imaging to telecommunications to data science. Fourth, and perhaps most importantly, studying black holes satisfies a fundamental human drive to understand the universe. We are curious creatures, and black holes represent some of the most extreme and mysterious phenomena we've discovered. Unraveling their mysteries enriches our understanding of reality and our place within it. The study of black holes also shows how science progresses. When Einstein published his theory of general relativity in 1915, he didn't set out to predict black holes. In fact, he initially doubted that they could really exist. It was only through decades of theoretical work, observational discoveries, and refinement of ideas that black holes went from a mathematical curiosity to accepted physical objects, and finally to things we can actually observe and study in detail. This process continues today. Every new observation of a black hole, every gravitational wave detection, every improvement in our theoretical understanding brings us closer to a complete picture of these remarkable objects, and each step forward raises new questions that push science forward. As we conclude our journey through the neighbourhood of black holes closest to Earth, let's reflect on what we've learned. We started with Gaia BH1, just 1,600 light-years away, a quiet black hole orbiting with a Sun-like companion star. We visited Gaia BH2, similar to its closer cousin but with a red giant companion. We explored famous systems like Cygnus X1, where Stephen Hawking and Kip Thorne's famous bet helped establish that black holes really exist, and V404 Cygni, with its wild and unpredictable behaviour. We journeyed to the centre of our own galaxy to meet Sagittarius A-Hyges, the 4 million solar mass giant that anchors the Milky Way, and we've discussed systems throughout our galactic neighbourhood. GRS 1915+105 with its powerful jets, GX 339-4 with its regular state changes, and many others. We've explored the physics of black holes, from the event horizon to the singularity, from Hawking radiation to gravitational waves. We've discussed time dilation, spaghettification, accretion disks, and jets. We've thought about the philosophical implications of black holes and imagined the far future when black holes will be the last massive objects in the universe. But perhaps the most important thing we've learned is that black holes, while extreme and exotic, are part of the natural world. They form through physical processes we understand. They obey the laws of physics, and they're connected to the broader story of cosmic evolution. They're not supernatural or magical. They're just regions of space where gravity has become so strong that it warps space-time in dramatic ways. The black holes we've discussed tonight are our cosmic neighbours, scattered throughout the Milky Way galaxy. Some are feeding actively, producing brilliant X-rays and powerful jets. Others are sitting quietly in the dark, detectable only by their gravitational pull on nearby stars. But all of them are part of the ecosystem of our galaxy, participants in the ongoing cycle of stellar birth, life, and death that has shaped the universe for billions of years. As technology improves and our understanding deepens, we'll continue to discover more about these fascinating objects. We'll find new black holes, measure their properties more precisely, and perhaps solve some of the outstanding mysteries that still surround them. We might even discover phenomena we haven't yet imagined. The journey to understand black holes is far from over. In fact, in many ways, we're still at the beginning. We've learned an enormous amount in the century since Einstein published general relativity, but there's still so much we don't know. What really happens at the center of a black hole? How does quantum mechanics modify the structure of the event horizon? Can black holes preserve information, or does it truly disappear? How did the first supermassive black holes form so early in cosmic history? These questions and many others will keep scientists busy for decades or centuries to come. And with each answer, we'll probably discover new questions we hadn't thought to ask. Black holes remind us that the universe is stranger and more wonderful than we might have imagined. They show us that reality operates according to principles that seem bizarre from our everyday perspective, but that make perfect sense when we look at them through the lens of physics and mathematics. They demonstrate that our universe is a place where the rules are clear and consistent, but where those rules can lead to outcomes that challenge our intuitions and expand our understanding. So the next time you look up at the night sky, remember that scattered among those visible stars are objects you can't see, black holes lurking in the darkness, warping space-time around them, some actively feeding and blazing with X-rays, others quiet and patient. They're out there, our cosmic neighbours, mysterious and powerful, waiting to reveal their secrets to anyone curious and careful enough to study them. Thank you for joining me on this epic journey to our closest black holes. I hope you've gained a new appreciation for these remarkable objects and for the incredible universe we inhabit. Until next time, keep looking up, keep asking questions, and keep wondering about the mysteries that surround us.